저기 우연아, 우연아,
우현이 형 지금 화장실 갔습니다.
상진이도 있구나.
네,
저기
네,
상진아, 내가 그 학생 면담이
네,
기회에 좀 있어서
네, 네.
그 2시 15분쯤에 시작하면 어떨까 싶은데.
아, 네, 제가 전달하겠습니다.
그래요. 고맙네.
네,
그래.
알겠습니다. 네.
Right. 보자. 지금 학생들 장진아.
네, 교수님.
저기 빨리 끝나가지고 지금 시작할 수 있나?
네,
다른
지금
학생들
시작해도 될 것 같습니다.
그래? Right. Let's start. This week we're gonna talk about the matching network. As you may understand, designing matching network is one of the most critical part in RFIC design. So this is basically you guys understand that for the matching, which one is important, resistance or reactance? Which one is important for the matching? So achieving matching is just to make a source impedance equal to conjugate of input impedance, right? So which one is important? Which one is more critical in designing matching network? Resistance or reactance? Who?
Yes, Professor.
Can you answer? Which one is more important?
Reactance more.
Resistance versus reactance. Which one is more important?
Reactance more.
Are you sure? Which part determine?
It means
which
the
part
real
of
part is
the
resistant, Professor.
Real of load impedance is resistance, right?
Yes, Professor.
So the resistance is critical, right?
Yes, Professor. Yes, Professor.
Yeah, resistor determine, the resistance ratio actually determine the quality factor Q, right?
Yes, Professor.
So the network quality factor determine the bandwidth, right?
Yes,
Of course,
Yes,
the network quality factor is just center frequency divided by bandwidth. That is actually 1 over fractional bandwidth, as we learned last week, right? So the ratio between source and input resistance determines quality factor Q, which means it determines bandwidth and it determines insertion loss, right? So that means the reactance part is actually easy to control, right? So let's just take a look at, when load is a complex impedance, okay? Let's say ZL is RL plus JXL, okay? We want to match GL to RS, and typically RS is just 50 ohm, right? So GL can be, input impedance of the MOS, right? Or something else. All right, in this case, right, we just we can always manipulate the XL part because it doesn't matter. It doesn't, contribute to determine the quality factor Q, right? So basically quality factor Q that we need to achieve is determined by this resistance ratio. Okay, then how about XL? Then XL can be just a part of total matching network, total reactance term of required Q. So, as we're gonna see next part, pi matching or T matching, sometimes when this reactance term is for example, capacitive. Even though what we want to get is inductive. Then, sometimes we just add another reactance term, which make a pi network or T network. Another times we can just observe this XL as a part of X matching. Okay, so in that regard, you can easily, manipulate, XL. So we just, set XL as a part of a total matching network. Then you just, add this inductance or maybe capacitance, depending on this one. If this is capacitive, then we may just add a capacitor. That's better, right? If this is inductive, then you do better to add a, capacitive term, like omega C, something like this, right? So it's depending on the type of, one you have. So next, you just calculate the X matching prime, right? So by choosing parallel capacitor such that this resonates out with this XL, X matching prime, then matching network is complete. Make sense? Okay. So this is a typical example, right? In this example, RS is a 50 ohm. The impedance is a 10 minus J 20, right? So in this regard, you just, at the beginning, right? GL is actually set to 10. Set to 10, right? But it has actually reactance term, right? So you just add a more inductor, right? So you add up this inductor. So for this one, right? If GL is a 10, right? What you need is this amount of inductance in parallel, right? But since you have a minus 20J, right? You need to make a plus J20. You add this plus J20 plus this L, right? This L, which make this inductance as 366 picohenry. Then you just use this is a series inductor. This is a parallel capacitor line. So just an improvement like this way. Okay. So another way of doing is the modification of L matching. Modify the L matching, right? How can we just modify? This is a similar, right? Previously, we did something like this. We did something like this, right? Instead of doing like this, which requires, more higher quality factor. I mean, network quality factor, right? It just use, reactance term to resonate out. So, for example, in this case, we add up parallel, inductance. So we just resonate out the capacitive part. For example, here we resonate out this, right? We just use this inductor to resonate out. Then it becomes, pure, resistive part. Then you just perform matching network. Now it becomes pi network. Okay. So since at this point, right? At this point, the effective R is larger than RL. So as a result, right, quality factor Q network is smaller than previous L matching network. So your bandwidth is improved. Understand? Okay. So another way. So this is a, let's say this is a high impedance line. So this is also capacitive. So in this case, we just, add a series inductance to resonate out. Then we move, this pure resistive part to designated, impedance using L match. Okay, so now it becomes T matching network, right? By doing this, we can just perform better bandwidth in case, it's possible. So another thing that you need to understand is that we want to get, lowest displacement. Okay, so lowest displacement means we want to use a, shortest transmission line length. Okay, or basically the quality factor, the equality factor, that is Q circle. Q circle is given by this. Q circle is given by this. Okay. Q circle is given by this. So as you can see over here, right? If the movement is relatively large, something like this, it touches, for example, here. It touches, right, the higher Q, which means the network Q becomes higher. This is X matching and R matching, which means if X is larger than Q is larger, right? Then that means your bandwidth is reduced. This is a fractional bandwidth. Right? That's what it means. So in designing any matching network, to achieve a wider bandwidth, you need to touch the lowest equality factor line. Okay, so this is how we get constant quality factor circle. So basically, we have the gamma is gamma real plus J gamma imaginary, right? So the gamma is actually distance between the center point to given position. This is a circle line, and this is gamma, right? This is gamma. So we can just as a magnitude wise line, we can just express like this way. Right? So if Qi is 0, then gamma becomes gamma real part can be plus minus 1. If Q is infinite, then total gamma must be 1. Right? So using this those condition, you guys can draw gamma R and gamma I as a function of quality factor Q. Then you can get this constant Q equality factor circle. So the design objective is to touch the lowest quality factor, equality factor circle. Then as you can see, right, if distance between this and this is the designated source impedance and this is load impedance. If distance is a long way, then if you just use a single matching network, right, then you need to use a higher quality factor, something like this, right? This is the only way you can achieve. Right? As a GL far away from GS, you might have a higher Q. To avoid this, you have to use a multi-sectional, matching, something like this. Then you can still track lower quality factor, which means your fractional bandwidth is improved quite a lot. Okay. So this is a design example, right? So let's say RL is a 5, RS is a 50. Right? Let's say you just want to design any power amplifier. Of course, if you use such a complex design, then total loss must be a little bit degraded, right? But anyway, more importantly, we are concerned on the bandwidth, then let's design. So here, desired ratio is 10, right? 10 minus 1 square, then it's a 3. Quality factor of 3 is required, right? So basically, you want to touch, this is a 1.5, maybe 3 is this. 30 must be almost around here. 3. This must be around 3. Okay, must be 3. Okay, this is actually what you will get if you only have a single section matching network, right? So, however, if you use multiple matching given by this, let's say I want to use a quality factor equal 1.5, which is almost twice improvement in bandwidth, right? Then how can I achieve it? So let's say in this case, we just want to use two consecutive matching network like this, right? So in this case, here I need to choose intermediate part, right? So using this condition, because we are just assigned quality factor in the same level, Q equal square root of L I and IL. Here L is 5, I is some value, and this is some value, L is 50, right? So based on this condition, we can easily get Ri by using the geometric average of 2. So it's 15.8. So we just move 5 ohm to 15.8. Next 15.8 to 50. Then we touch just 1.5 position, right? So the network quality factor Q is 1.5. So fractional bandwidth is improved by twice. Okay, there is a rule of thumb. If the wanted quality factor is less than half of a single quality factor. For example, if you want to design matching network with a quality factor equal to 1, which is less than 1.5, which is 3 divided by 2, right? Then you need more than 2 stages. Definitely maybe 3 or 4, depending on your design. Then you cannot apply this, right? You have a more complex equation. So, yeah, but it's not that difficult. You can easily get, by drawing, this Q factor line, then you just move step by step, move step by step like this, right? Maybe if it's there, then move step by step. So if it's something like this, then you just move here again, move here again, move here again, move here again, right? Maybe 5. Okay, that's not that bad. That's not that bad to design. However, for the two cascaded L matching network, you can use this equation. Okay. All right. So here is a more generalized expression. I just derived it, but make sure this is applicable to everywhere. I'm not actually sure. So okay, let's take a look. When for the single stage L matching network, right? So if RL is 15 and RS is 50, then Q network is 1.527. If I want to design equal 1, then it's divided by 2 is a point around 0.75 or something, right? Which means at least I can just design multiple matching network with a 2-stage. Okay. The rule of thumb is this. So Q network has to be, the ratio scaled by 1 over m. M is the number of stages. Okay. So in this case, right, Q network scale plus 1 to the m should be larger than this. This RS and RL ratio is just what, 50 divided by 15, right? So if you put, this is just an integer number, right? So if you put 2, right, then 4 is larger than 3.3, which is 3.3. So maybe, you may just use 2 stages, okay? If Q net is less than 1, right, or maybe 0.5, then you may need more stages, right? So just use this, okay, to see how many number of stages are required. Okay. So this Q net means, input impedance varies by 3 dB. Okay, but this is only true for single resonant network. Okay. Actually, this is a definition of Q line. Q is a fractional bandwidth, right? This is a 3D bandwidth line, fractional 3D bandwidth. That's what I mean. But this is true only for single resonant network. That's what I mean. Okay. And previously, we also talked about how to achieve, very simple transmission line based matching network by using quarter wavelength transmission line. So quarter wavelength means wavelength L is lambda over 4. Right? In this case, by using this equation, right? Oh, I'm sorry. By using this equation, right? Once beta is just lambda over 2 pi and L is lambda over 4, which is just pi over 2. So the tangent beta L becomes infinite line. So you just divide this by this. So eventually you get G naught, and here you have a G0, and here you have a JGL, right? Which is a G in. Therefore, what you get is G0 square is a GL multiplied by G in, right? Therefore, required G in is the square root of GL G in, right? That's this, right? Okay. So, to make a matching between G1 and RL, you choose a G not equal to GRL multiplied by G1, okay? That's the one you achieve. This is actually widely used. And sometimes we call this as a impedance inverter, right? Impedance inverter. Right? Impedance inverter, because this load is inverted. Right? For example, if this is let's say capacitive, the input impedance is seen to be inductive. If this load is inductive, the input impedance is seen to be capacitive by using this quarter wave transform. That's very useful. Another way to achieve is, this is an extended version of a previous design. In this case, this impedance is complex. So RS plus minus JXS, and load impedance is also complex, RL plus minus JXL. Then you can just make a matching between two by controlling characteristic impedance and zeta. This is very powerful because you can achieve an interstage matching using only single T line. This is very amazing, right? However, we notice that based on this equation, right? If RS is same with RL, then GL is infinite. Okay, you should not use a single transmission line matching network when RS equal to RL. It's impossible. That's true. Why? Because of this. Let's say XS and XL is 0. Then if RS equal to RL, you don't even need any matching network, right? That's why it doesn't have. Also, zeta is the same. If RL and RS is same, then zeta is 0. Okay, so for this single cascaded transmission line matching network, you should not use when RS equal to RL. Other than that, you may find a good solution between interstage. And also, this can be useful when you design, the power amplifier. When you connect the two, HEMT, right? Let's say this matching network for the power matching line, the required impedance is G opt, right? And this is also G opt. But unfortunately, if G opt is much, much smaller than G naught, GL, which is typically 50 ohm. This is getting worse, right? If you just naively connect this together, this is a half of G opt. This is very bad, right? Then you may have a trouble with achieving, matching network with a low loss, right? Because the Q ratio is, the resistive ratio is too high. Then you may use this cascade transmission line. Anyway, whenever you route between this and this, you need a certain length in connection, right? So you just choose proper G naught and proper zeta from this and this equation. Then you may just achieve this point as a middle part. For example, let's say this is a 25 ohm, which is a half of 50 ohm, right? Or maybe this can be 15 ohm, which is much better than just to achieve a 2.2 to 50 ohm matching. Let's say this is a 5 ohm, required optimum resistance is 5 ohm. Then total, if you just connect together, naively connect together, then it becomes 2.5. This is too hard to achieve match. But if you use this transmission line and this length properly, then you may just achieve at this point you may achieve 25 ohm matching, right, with a JX summing. Then it doesn't matter for this. This can be always observed. And you can just easily achieve matching network with a 1.4 Q equal 1.4, which is wide enough. Okay, you guys understood? 태훈아 이해했냐?
네, 이해했습니다. 네.
Okay, here is a homework. So find the characteristic impedance TL and zeta using single cascade transmission line to matching two compressed terminations. So the question is here, right? You just use the previous equation. That's it. Okay, right? Then you just choose a zeta and TL. Okay. The second one is just option. Okay. Maybe Sangjin and Taeun must be interested in this. So design routing transmission line connecting two 6 by 150 micrometer HAMT with a G opt equal to 16.6 plus J 23.3 in achieving XL equal 50 minus JXL. Okay, where load admittance can be chosen arbitrarily. So since this is a something like this, right? So just consider single matching. So what you need is actually 16.6 plus J 23.3, right? And another thing that you need to be very careful is that you just implement this using termination. I mean the port network, port, right? Port. Okay. So unfortunately, even you achieve, by achieving this L matching network, you can just achieve a 16.6 minus J 23.3. It doesn't guarantee that this is matched. You understood, right? Because 그러니까 중요한 이야기니까 내가 한글로 할게. 그러니까 여러분들이 파워 매칭을 할 때 있잖아. 파워 매칭을 할 때 여러분들 조심해야 되는 게 파워 매칭은 컨주게이트 매칭하고 달라. 그래서 이거 50ohm을 가지고 여기서 이렇게 L 매칭을 하든 뭘 하든 해갖고 여기 원하는 16.6 마이너스 J23.3을 만들어도 있잖아. 여기서 봤을 때 이게 50ohm이 보이지 않아요. 그거 알고 있지? 태훈아 알고 있지, 그지?
네, 알고 있습니다.
왜냐면 이게 컨주게이트 매칭이 아니기 때문에 그래. 여기는 뭐가 들어가냐면 햄트가 들어가. 햄트 임피던스는 이게 아니란 말이야. 그래서 여기에 자연스럽게 리프렉션이 생겨서 여기서 보이는 게 우리가 기대하는 50ohm이 아니야. 그래서 경우에 따라서는 그 파워 앰플리파이어의 S11이 좀 나쁘게 나와. 알겠지? 적절하게 선택을 해야 돼. 그래서 그거 빼고는 지금 여기서 이야기하는 이슈는 뭐냐면 여기서 그냥 이렇게 보란 말이에요. 이렇게 여기서 이거를 합성을 해. 16.6ohm이 되게 매칭 네트워크를 만들어서 합성을 해서 이걸 여기서 이렇게 보이게 그러니까 이게 두 개를 붙여야 되니까 이거 두 개를 이렇게 붙여야 되잖아 지금 이렇게 두 개를 이렇게 붙여야 된다. 그지? 그러면 여기에 적절한 임피던스를 만들어서 이게 두 개를 코먼 모드로 붙이면 얼마가 되냐 이게 하프가 되지 하프가 이게 하프가 돼 여기서 보이는 거. 만약에 이게 없으면 여기에 임피던스가 엑스트라로 없으면 맞지 태훈아 그지?
네, 맞습니다.
네, 맞습니다.
그런 식으로 물론 이제 여기 있어 인덕턴스 있으니까 이게 이제 컨트롤 되는 거야 이제. 그래서 하여튼 적절하게 요 길이를 선택을 하라는 거야.
네네.
요걸 고려해가지고 여기 거의 물론 이 길이 때문에 스케일링이 되겠지만 뭐 이렇게 갈 거 아니야. 이렇게 전송 둘러가 이렇게 바로 붙게 이렇게 갈 거 아니야.
네, 맞습니다.
요 프렉스를 봤을 때는 하프란 말이야. 보는 게 하프란 말이야. 이해했지, 그지?
네네.
그러니까 요렇게 봤을 때가 그러면 요게 지금 어떻게 되냐면 이게 100옴으로 봐야 돼. 이게 50옴이 되잖아. 50옴이 되면 이거를 두 개로 코먼 모드로 보이기 때문에 이걸 반으로 쪼개면 얘 입장에서는 보면 이렇게 되는 거야. 이게 매칭 네트워크고 이게 100옴이 돼야 돼.
네, 맞습니다.
이렇게 된다. 이렇게 매칭을 만들어 놓고 그지? 이렇게 붙여야 된다. 그러니까 이걸 이렇게 하지 말고 이거 한 반 정도로 스케일링해서 여기서 다시 매칭을 만든다고 생각하고 이걸로 다 하진 못하니까
네네.
이거를 스케일링을 이거를 쓰란 말이지.
네네.
이렇게 적절하게 이렇게 하든지 뭐 해가지고 그지?
네네.
그래서 한번 해봐. 이게 그래서 4개 패러렐을 하는 것도 뭐 내가 하지 말라는 건 아닌데 2개로 한번 만들어 봐요.
네, 알겠습니다.
그래서 5와트도 똑같아 상진아. 5와트도 2개로 하는 것도 괜찮고 1개로 하는 것도 괜찮아. 1개는 조금 빡셀 거니까 뭐 2개로 한번 해보든지. 알겠지?
네,
네,
알겠습니다.
4개짜리로 2개로 하면
알겠습니다.
정말 빡셀 거야. 그래서 태훈이는 뭐 옵셔널로 한번 해봐. 알겠지?
아, 네네.
Alright. This
교수님
is
혹시
an example.
질문 하나만 드려도 되겠습니다. 그 앞에서 Q 맞춤 매칭 할 때 그 첫 번째 임피던스 지점이 그 높은 Q 값에서 찍히면은 어떻게 해야 되죠?
아니지. 그게 어떻게 되냐면 네가 선택하는 거야.
아,
이게 멀티플 매칭을 하잖아.
네.
그럼 이 그림을 그려야 Q가 예를 들어서 이게 내가 원하는 Q 이꼴 뭐 1이라고 쳐요.
네.
그럼 내가 여기에 있잖아. 여기 예를 들어서 뭐 내가 여기 정도 좀 있다고. 뭐 여기에 네 말은 여기에 이렇게 있다고.
네, 좀 더 높은 막 원 끝 지점 쪽에 있어요.
높은 Q의 끝 지점에 있다고.
네네.
그거는 불행히도 답이 없어.
아,
그건 답이 없어.
그러면
그거는 어쩔 수 없이 아마 넘어갔잖아.
네네.
왜냐면 이게 본래 네트워크 Q가 사실은 자기 자신의 Q에 의해서 결정이 되기 때문에 그래. Q라는 게 결국은 리지스트의 리액턴스잖아.
네, 맞습니다.
그래서 이게 적으면 이것도 작아야지. 이게 적은데 이게 크잖아. 그럼 답이 없는 거야.
아,
그때는. 그러니까 보통은 근데 그렇지 않아. 보통은 이게 이제 보통 이제 이 트랜스포머로 이제 보통 이제 R이 스케일링 되는 거니까.
네.
이렇게 있으면 뭐 그건 답이 없는 거야.
그러면
이미 한번
설계를
넘었는데
다시
이렇게 있다. 여기 이렇게 있다. 이건 답이 없어.
아,
레조네이트 시킨다 해도 답이 없는 거야. 이거 레조네이트 시켜. 내려오면 벌써 아마 얘를 터치했잖아.
네.
그건 답이 없어. 답이 됐을까?
네, 답이 됐습니다.
이 네트워크 Q는 이 Q보다는 어쩔 수 없이 이렇게 커질 수밖에 없어요. 원래 인트린직 Q. 이건 어쩔 수 없는.
알겠습니다.
언제나.
교수님, 제가 또 하나 본 게, 제가 그 햄트 디바이스에서 그 게이트 위스를 넓혀가지고 로드풀을 돌려보니까요. 그게 그 최적의 그 출력 임피던스하고 그 효율 임피던스하고의 Q 값이 엄청 커지더라고요.
음,
네네. 그래서
값이 볼륨이 크다.
네, 저희가 보통 사용하는
그럼 답이 없어.
네네. 그래서 이게 Q가 한 저희가 보통 쓰는 게 지금까지 설계했을 때 6 곱하기 한 120에서 6 곱하기 150 정도 했는데 이번에 제가 8 곱하기 250으로 확 늘리니까요. 그 Q가 한 3.5에서 한 5 정도까지 늘어나더라고요.
그게 아마 그게 그럴 수 있겠다. 왜냐면
네, 교수님.
그게 캐피스톤은 그냥 패러렐로 하든 뭘로 하든 그냥 대해지는 거잖아. 하나
네,
전체로
맞습니다.
둥근해서.
네네, 맞습니다.
거기다가 이제 저항은 적어지니까 Q가
네네.
커지겠지.
네네네.
그러면 일단 그렇게 하려면 밴드위스가 리미터가 되겠지.
네네네.
밴드위스를 좀 리미터하고 해야지 설계를. 근데 Q가 3이라도
네네.
프랙셔널 밴드위스로 따지면 그렇게 나쁘진 않아. 사실
아,
솔직히.
네네네.
왜냐면 Q가 3이면
네네네.
10기가에서 프랙셔널 밴드위스가 3.3이라는 이야기야.
네네, 맞습니다.
어. 그러니까 3.3이면 3.3기가인데 그럼 뭐 나쁘지 않지. 사실 그걸로만 다 치고 한다면.
네네.
그래서 우리가 뭐 그냥 9에서 10기가만 만들면 되잖아. 1기가만 만들면 되잖아.
근데 그 대학 포기야, 네. 1기가만 하는 거예요. 네.
그렇게 중요한 건 아니니까.
4까지
그래도 한번
했던 것 같긴 합니다. 노트를 돌려보니까요. 네. 그래서 Q값이 너무 이렇게 높아가지고, 네. 약간 애로사항이
적합한 값을
있었거든요. 네.
찾아야 돼.
아, 네네네.
그래서 일단 Q가 지금 우리가 사실은 이제 프랙셔널로 따지면 10이잖아, 10.
네네네.
그거의 반으로 따지면 5고, 그다음에 이제 그게 또 Q가 또 실제로 매칭 네트워크에 로스가 있기 때문에
네네, 맞습니다.
실제 이펙티브 Q는 또 줄거든.
아, 네네.
그래서 한번 만들어 봐요.
아, 네, 알겠습니다. 네네.
안 되면 이 방법을 써서라도 옵티멈하게 랭스를 좀 줄일 수 있는 방법을 찾든지 밴드위스를 넓히는 방법을 찾든지 조금 더 옵티마이제이션 한번 해보게.
아, 네, 알겠습니다.
일단 우리는 이거를 이제 카드로 쓸 거고
네네네.
하나에서 이제 이야기를 하면 내가 이제 대응하는 방안은 그 양반들 목요일 날 온다고 하거든.
아,
그러니까 그거 관련해서 좀
네네네.
자료를 준비했어야 해.
네네네.
목요일 날 오면 그 사람들 그 발표한 거 있잖아. 그 개인 저기 그 1인 기업 거기서 발표한
네, 교수님.
거 있잖아. 그게 이제 디임베딩 이슈.
아, 네네.
어, 그 이야기를 내가 집중적으로 이야기를 하려고 그래.
아, 네네네.
그래서 이제 만약에 걔들이 DS전자에서
네네.
1인 기업에서 만든 전력 정폭기를 측정을 해서
네네.
진짜로 걔들 말한 성능대로 나오면
네네.
그게 우리한테는 최악이야, 그지?
아, 네, 맞습니다. 네네.
그게 우리한테는 최악. 그러면 그 진짜 해줘야 돼. 그런데
네,
만약에 그게 아니다. 걔들 디임베딩 한 것만 가지고 지금 그런 이야기를 하면 나는 그걸 인정하지 않겠다는 거야.
네네네.
그러면 그 근거가 뭐냐 이렇게 나올 거 아니야.
네네네.
그러면 그 근거를 매칭 네트워크 기준으로 얘들 이야기하는 대역폭을 보니 우리하고 대역폭이 비슷하더라.
네네네.
대역폭이 비슷하다는 거는 Q 레이쇼가 비슷하다는 거고 Q 레이쇼 비슷하다는 거는 매칭하는데 뭐 별거 없잖아.
네네네.
달라질 게 없다 이거 달라질 게.
아, 네네. 맞습니다.
그렇게 이야기를 하려고 그래.
아,
그래서
네네.
한 가지 우리가 간과했던 거는 이렇게까지는 안 했잖아 우리가. 이렇게까지는 안 했잖아.
아, 네, 맞습니다. 네네.
트랜스미션 라인을 커넥션에 쓰는 거는 안 했잖아.
네네.
그걸 한번 해봐.
네네, 알겠습니다. 네.
4개로 해봐. 상기는 2개로 해봐. 알겠지?
네,
커넥션.
알겠습니다.
그렇게 해서 로스가 줄면 그럼 우리가 하고 있다 이러면 되는 거고 안 줄면은 걔들 한 거 증거로 내놔 이렇게 이야기하면 되는 거지.
네, 알겠습니다. 네.
그렇지? 우리도 살아야 되잖아.
네.
그래. 오케이. Okay, so let's move to stub matching. Okay, so this stub matching is the most widely used matching mechanism in the microwave design, microwave circuit design, right? So different from the lumped component matching, it just utilizes a transmission line as a matching component. Because if you just add up series transmission line, right, with the L, then this just in the Smith chart, right? The Smith chart, it just move your pointer to clockwise by 2 beta L, right? So by using this, you can control the impedance, right? So also, if you add a shunt component, which is just the same, if you C is just JB, right? Just add up JB over here. So we just find let's say the impedance seen at this is minus JB. You just make a synthesize a JB to resonate out this minus JB, right? This is how we achieve with the stub. So this is a procedure. Here we want to design GL matched to 50 ohm. So this is very straightforward, right? So for example, let's take a look at, because you guys are not undergraduate student, right? So basically, you may just use design itself is more important. So you may just use a Smith chart, right? So the example, let's take a look at the example. So here, operating frequency is, let's say this is 3 gigahertz, right? So let's say this is operating frequency is 1 to 3 gigahertz. So we choose 2 gigahertz. Here, setting, it's just use 2. Okay, so we just plot impedance as 60. This is a minus 80, right? So here, right? And we just add a transmission line, right? So there are 2, match the point, right? One is this, right? And we also add a shunt. In this case, let me see which one. Typically, I use open network, but in this example, they use a short net, short stub, right? So let's use a short stub. So this is short stub, right? Since the short stub is basically inductor, right? Inductor is going this part, so it's better to use a short stub. So this is a GL. This is a okay. This is wrong. I have to use this connection, right? So let me just use this. Okay, just go this part, right? You have to go this part, right? Because this is shunt. So I have to choose this short stub, which is going up. So this way. So this is the way how we achieve a matching. Right? In undergraduate course, right? We just actually draw this on top of the Smith chart, right? We just to understand the basic concept. So, okay, let's take a look at another way, right? So here, if I extend the line by this amount, which one is better, open or shunt? Definitely, this must be better, right? If you use open stop, the length is just 1.1552 lambda, right? Okay. So another option is, what if we use a shorter stop? If you use a shorter stop, we move by this here, right? Then shorter stop must be very long, very, very long. You just move this amount, right? Okay, so as you can see, if your required stop is your required shunt stop is before resonate out, your impedance is reactive. Your impedance is inductive. You have to use capacitive shunt stop. To achieve capacitive shunt stop, what you have to use is open stop, not short stop. In the same way, like this way, if you want to if you want to achieve, if you want to add a inductive inductance to make it resonate, you have to use short stop to achieve shortest stop length. Another important observation is that whatever it is, the shorter the stop, the lower insertion loss. Okay. Second, do not try to use shorter stop. Open stop is always choice one. Why? Because if you use shorter stop, you have to make a beer, right, for the gallium nitride. However, this is different for the CMOS design. For the CMOS design, right, you place ground plate all over the place. So it's also easy to achieve a short stop as well. Okay, so there is no, limiting factor in the CMOS design. Make sense? Yeah. Who? Make sense?
Yes, Professor.
Okay. So what did I say? If desired inductance, a desired resonant component is inductive, which one do you have to use? Open stop or short stop?
Open stop.
No.
Sorry, can you sorry.
Okay. You need if you need inductance, you need inductance to make it resonate out, to make a reactance resonate out, right?
Yes.
If
sir.
you want,
Yes, sir.
if you need inductance to resonate out, which one has to be used? Open stub or short stub?
If we need inductance to make resonant out, please should use the short stub.
Short stub, right? Because
Yes,
the short stub means it's an inductor, right?
Yes, Rosa.
Yeah. Open stub is naturally capacitive, right?
Capacity.
Right?
Yes, Rosa.
Yeah. So as can be seen here, right? So if length is longer, then you have a narrow bandwidth, and loss is more involved. Okay. So this is an analytic formula. It doesn't matter. Okay. So double stub matching. This is actually not widely used in modern circuit design because it is more lossy and doesn't do much. But let's take a look at the the effect. Okay. So basically, for the double matching, right? For the double stub matching, right? You just have a one more degree of freedom. So, for example, by controlling D, right? By controlling D, you can just place a matching network at arbitrary position. Okay. So, however, there exists a forbidden region that cannot be matched theoretically. Okay. So let's take a look at what's going on. For this example, right? Let's say you have a YL, and so basically double stub matching is just something like this. If you add this amount of transmission line, right? You move your impedance by phase of 2 beta D in Smith chart, right? So what it means is that you just, or in this example, you just choose D as a, just a pi over 2, which is a lambda of 4. If you just choose, in this case, this is a 90 degree, right? 90 degree means 0.25 because of one circulation is just a pi. So half circulation is pi of 2, right? And quarter circulation is pi over 4. To make a pi over 4, beta equal pi of 4, beta L equal pi over 4. So let's just it's something like this. 2 beta L is let's say 2 beta L is this line. So L is just 2 beta multiplied by pi. This is just lambda 2 pi and this line. So this is what? Pi over 8, right? If you choose a length of D is pi over 8, right? You just arbitrarily move from this to this amount, this to this amount. Okay. So let's say this impedance is Y1, and let's say this impedance is a Y1 prime. So basically, this length is moving this y1 to y1 prime, this to this. Okay. So what it does is that we just, in choosing this transmission line, right? In choosing this transmission line, we just assume that it's gonna be moved back in counterclockwise. So we intentionally, rotate this to this circle by 90 degrees. In this way, since we know the designated, matching point, we just, design the L2, and once we understand once we resonate out this amount, then you just arbitrarily choose L1, then you can just design all matching network. So here is an example. So plot the normalized Y like this, and draw corresponding stabilized circle, which track this phase, right? Find the two intersection point where 1 plus JB meets this stabilized circle, right? And rotate this, right? But unfortunately, we cannot rotate in the Smith chart, right? In our Smith 4.1. That's why I don't use them. Okay, just move, the cross the the intersection to counterclockwise by lambda over 8, pi over 8 actually, pi over 8. Okay, pi over 8 is 90 degree. Pi over 8 is 90 degree. This is same. Lambda over 2 is 360. Lambda over 4 is 180, and 8 lambda over 8 is 90 degree. That's the same meaning. Okay, same meaning. So okay, this is correct. Okay, so the wavelength D is lambda over 8, right? Lambda over 8. Okay, so we just move this by lambda over 8 like this. Lambda over 8, then this intersection point, two intersection point, this and this, right, is just this is a move to here, and this is a move to here. Okay. Okay, so move load to B0 prime by adding open stop socket. Right? So because this is an open stop socket, we just synthesize in G Smith chart, which is an open stop socket. In G Smith chart, this is the point open. Right? And just make a L1, make a L1 to rotate, right? So once you do that, then you just choose a 2.1 and 2, and move this to here, 90 degree, and move this to here, 90 degree. Okay, and this is a load, and you just choose this, which is a P1 prime. Okay, P1 prime. Okay, once you choose this, then you just once you move this line, once you move this, at this point, if you move back to here, right? If you move back to here, you have to meet here, which is resonate out with this. And since this is moving back by plus 2 beta L, this point gonna be back to here. So you just add this resonated circuit, which is this amount, then you achieve. Okay. 그러니까 간단하게 이야기하자면 더블 스톱 매칭은 얘가 지금 실제로 여기하고 그다음에 여기하고 붙는 요 1 플러스 JB 지점을 여기로 옮기잖아. 여기로 이렇게 옮기는 거란 말이야. 이렇게 옮기는 건데, 그러니까 내가 지금 여기 입장에서 봤을 때는 요 로드가 여기 입장에서 봤을 때는 요렇게 움직여야 돼. 요렇게 움직이면 그러니까 요 지점에서는 여기거든. 왜냐면 이게 이전이거든. 여기에서 지금 거꾸로 갔잖아. 거꾸로 갔으니까 이 지점에서 움직여야 된다고. 이 지점에서 여기서 이렇게 움직이는 게 아니고 이 지점에서 이렇게 움직여 놓고 여기가 붙으면 여기서 이 베타 D만큼 다시 움직이면 이 붙은 게 이쪽으로 간단 말이야. 이해했지? 그래서 이렇게 가도록 어떻게 만들어? 요걸 붙이고 요걸 붙이면 이렇게 간단 말이야. 그래서 여기에 8분의 남다를 움직이면 요게 다시 여기로 온단 말이야. 그럼 내가 원하는 대로 왔잖아. 그러면 요게 요 지점이란 말이야. 그러면 여기서 요만큼을 요걸 붙여. 그러면은 다 매칭이 된 거지. 이해했냐? 우연아 이해했냐?
네, 알겠습니다.
그러니까 이게 이제 디그리 오브 프리덤이 왜 있냐면 이 위치를 내가 이건 지금 8분의 남다로 이제 계산하기 좋게 그냥 한 거지만 이걸 내가 아비트러리하게 만들 수 있다는 거야. 아비트러리. 이걸로. 그리고 또 하나가 이 값이 아니더라도 이거를 실제로 이렇게도 만들 수 있어. 이렇게 아비트러리하게 만들 수 있는 거야. 같은 방식. 두 번 옮기면 되잖아. 두 번 옮기면. 그지? 됐죠? 뭐 요새 우리 매칭 네트워크 안 써 잘. So okay, now take a look at the impedance matching of balanced circuit. So let's assume we want to achieve matching between two amplifiers. Okay, so in this case, G out is 10 ohm and G in is 100 ohm in differential form. Okay, so how can we achieve matching? This is very straightforward, right? We just for the differential, right? We can just bisect. We can just bisect and consider single-ended equivalent, right? Equivalence. Then this is divided into two parts. This is a 5 ohm and this is a 5 ohm. Totally 10 ohm. Differentially 10 ohm, but in single-ended it's a 5 ohm. This is the same, right? Differentially 100 ohm, single-ended 50 ohm, right? Just to make a ground over it. So in single-ended form, this is just a matching between 5 ohm and 50. Okay? Then you just make an L matching network like this, right? So L matching network like this, L matching network, which is a reflected form, right? Which is exactly the same. Then we just add up this, right? This is in series, so this becomes this, right? So eventually we design like this way, 2.8 nano and 5.6 pico and 2.8 nano. The balanced matching is done. Okay, very simple, right? Okay. All right. Now take a look at matching network using transformer. Okay. So basically, for the AC analysis, right, you can always use a T equivalent circuit. You notice that this T equivalent circuit is valid only for AC network, not DC network. But it doesn't mean that there isn't any mutual coupling, mutual inductance in DC, right? Actually speak, mutual inductance and inductance, all of them can be defined even in DC, okay? Mutual inductance is actually M12 is defined I2 and flux linkage over 1, right? So which is actually I2 and flux linkage 1 and flux 1, 2 and DS, which is actually, this is P2, right? P2, which is actually, let me just rewrite. Okay. So as can be seen, even in DC, it can be defined. It can be defined, right? Whenever I conduct, there exists the B, even at DC. So mutual inductance also can be defined in DC. Okay. However, what I want to say is, if you want to use T network, this cannot be applicable in DC. Why? In DC, right, this is a short, this is a short, this is a short. Everything is a short, but in real circuit, right? In real circuit, this is open. It is not connected between this port 1, port 2, port 3, port 4. Between port 2 and port 3, right? This is open. Understand? However, in the analysis, you may just use this, right? By using G parameter expression. Okay. So typically we model transformer using 5 parameters. 5 parameters like this. And resistor and 5 parameters. Resistor, and this is 1 minus K L1, and this is a K L1. Total, it become L, right? L1, right? And there is a real, ideal transformer. Ideal transformer, 1 to n ideal transformer. Okay, and this is K, and this is a 1 minus K and L2, and this is R2. Okay, so in this case, if you want to make a resonance, XL is just a XL, which is connected to here, right? XL is just a minus omega L2. XS is also minus omega L1, just to resonate out the inductance. Okay. And how about R? R is just calculated by this, which is actually close to R2KQ. Okay. Because typically K1, Q1, and Q2 is similar. So let's say this is the same. And K square root of K is just K. So this is this. Okay. RS is same. RS is also R1 KQ. This is very interesting, right? Which means, if you achieve, if you want to make a matching network using transformer, it is almost impossible to achieve, resistance matching. This is just nothing but a resonator, actually. Frankly speaking, it's a resonator because this is really difficult to achieve. How can you control K and Q? Fortunately, if you draw the mismatch as a function of K and Q with respect to RS, it doesn't matter. It doesn't make any big difference. That's why this is working, okay? Another thing. So as you guys observed, right? This, if, the ratio N is given by, actually given by, L2 divided by L1. If you want to achieve, large N means Q1 and Q2 is different, and which is very, very difficult to control. Also, resonance frequency is reduced. This is also very bad. And moreover, Q is reduced, which means, the insertion loss is directly proportional to Q square, K square Q1, Q2, which is a, figure of merit of transformer. Therefore, it's always better to keep N close to 1 to achieve, optimum insertion loss and, okay, then how can we make N close to 1 without changing many things? The easy peasy way is just to add up capacitor in parallel with RL. This is a very, very natural, right? Because N is actually N scale R1 is RL, right? If you want to reduce this L, this N, right? You need to reduce RL. So the effective RL, by reducing effective RL, you can reduce N. How can I reduce effective RL? Just add a capacitor. If you add a capacitor, right, RL parallel with SCL this way. So this is RL plus SCL and SCL RL. So eventually this is 1 plus SC RL and RL. So this is reduced as the frequency goes high. Reduced effective. Make sense? Since this is reduced, you can reduce N. Okay? So this is the most widely used configuration. Also, our lab utilize this very frequently. Okay? So you just to reduce turns ratio, you just add a capacitor, right? Then you can just make this parallel network into series network. So here R equivalent is what? R equivalent is what? 1 plus Q square invert R parallel. So since you made the Q high, right, by adding CL, right, which means R equivalent is reduced. Okay, so once you get R equivalent and X equivalent like this, as you can see, it is reduced, right? Using those, equivalent, R equivalent and X equivalent, you can also get this R opt and C opt. Eventually, what you can see is this is the same as before, and this is added. Okay. But as can be seen here, right? This is a what? This is a let's say this is a very big. This is a cross 1, then this is actually k square q1, q2, and q2 square, which is eventually 1 over k, right? So which is if k is close to 1, and this is just increased by half. Okay. And CT opt is also given by this, which is eventually scaled by k square plus 1 L2. Previously it was just omega square L2, right? C was just changed by this amount. Okay. So the optimum value for this parallel configuration is given by those, right? Very simple. So here we assume Q1 and Q2 are almost the same, and K scale Q1, Q2 is much larger than 1, right? Then the optimum source and load impedance in series form can be given by this, right? This is what we observed, right? Also, for the optimum source and load for impedance in parallel form is given by this. Okay, so by taking a look at this, right, K is changed to this. Okay, and C is changed to resonate with this. So L1 plus K square. Okay, that's it. So here we make an analysis of the intrinsic insertion loss. So basically, this intrinsic insertion loss is given by 1 minus this factor. As I said before, right? K scale Q1, Q2 is a figure of manifold transformer. The higher this value, the better transform you achieve. Okay. So in this case, if K scale Q1, Q2 is much larger than 1, it is given by this. So that means you need to increase K, or you need to increase Q to reduce insertion loss. Okay. Be noticed that GT max is always less than 1. So in order to make this close to 1, this has to be close to 0. Makes sense, right? Okay. So here are the interesting factors in transformer-based matching network. We can see that primary and secondary coil inductance should resonate with the source and load capacitance by scaling L with the L1 plus K square for the parallel RC network. Right? Also, it's very interesting that optimum CS and CL are only a function of L1 and L2. Okay. So as can be seen over here, right? If it is in series resonator, then K doesn't matter. But if this is a parallel resonator, then K is involved like this. Okay. Therefore, it is very important to control K. This is the most critical part in designing transformer. Of course, it's very difficult to control Q, I understand, but at best, you have to control K. Otherwise, your design will be failed. Okay? That's why we always use HFSS. Okay? Also, equation T11, this T11 is valid, right? This is not valid when n is larger than 1. We assume, n is 1, right? Because of this assumption is used. If n is different, we have to use original equation, or this original equation. This original equation, okay? Make sense? So also if RL is much larger than RS, then we need a more turns ratio N. We need to add a parallel capacitor, right? That's what I mentioned. Okay. Now, this is a new, material, Norton transformation. Sometimes you find, that we need to change the load value, but we don't want to change performance. For example, we want to keep the bandwidth exactly same, but load impedance is changed from RL to R prime, right? If you just design without Norton transformation, then you might have a different, quality factor Q, which means a different bandwidth, different frequency response profile. So to avoid this, right, we may use Norton transformation. By using Norton transformation, okay, you can rearrange circuit topology without changing the order and response of the circuit, frequency response and circuit. Okay, this is very important, right? Without changing, the order of number of poles, without changing the frequency response, still you can apply different load. You can use different load with the exactly same performance. Okay. So depending on the configuration of component pair, the transformation may be used to increase or decrease the impedance level at one side of circuit without affecting the impedance at second side. Well, let's take a look at this example. The initial design, I used RL equal to 12.5. Unfortunately, I had to move RL as 112.5. How can I use this impedance without changing the performance? Since RL is larger than RS, right? Definitely we have to switch this to this, right? This is the first thing that you have to do, right? Basically, you have to, I think this is wrong. This figure must be opposite, okay? This figure must be opposite. So I think this must be 112.5, and this must be 12.50, okay? But this is not that important. And basic idea is same. We follow the same, design concept. Okay, so we just swap the direction of L matching network. Okay, we swap direction of L matching network, right? Because this inductance is larger than this. Definitely, this part, this must be here, right? But anyway, let's assume this is correct, right? Then we scale down. We scale up Ls by this square root of n, Lp by square root of n. Here n is actually given by this. Okay, so n is actually given by L series plus L parallel divided by L parallel. In this example, n is 9, okay? When n is 9, you may just convert like this way. RL is n by RL. LS is square root of NLS. LP is square root of NLP. Okay. Then how about, what if n is different from 9? What if n is 4? How can you do this? Okay. Then there is a way. For this example, right? We just look at this. This is correct. Oh, okay. Actually, I have to check this. Okay. So in this example, I want to make a k equal 4, n equal 4. Okay. So RP is given by 5, right? LP is now LP is what? LP is given by 5. To make this equal to 4, I have to use a series inductance as a 5. Previously, it was a total, it was a 10, right? So I just segmentize into 2 sections. One is LSA. The other is LSB, which is required to achieve 4, k equal 4. Okay. Then I just leave 5 nano as it is and convert this to this part. Okay. Then it becomes T matching network. And eventually, this is 4 multiplied by 50. So this is k equal 4, right? So 4 multiplied by 50 and 200. Okay. So the second, there is a second option. As we just split series network, series inductance, we can also split parallel inductance, right? Because this is split in admittance domain, right? The susceptance domain, right? We just calculate like this, right? So we just to make a 4, to make k equal 4, we just make a LPA equal 10 nanohenry, and this is also 10 nanohenry. LP equal 10 nanohenry. Then 10 plus 10 scale is 4. So same, right? So we just this part as it is, we just swap this as a square root of k and just multiply this by n. Okay, like this. So inductive transformation is done. 이게 매칭이 좀 이상하다 이거. 이게 매칭 이렇게 하면 매칭이 안 될 텐데 이게 거꾸로 돼 있어요 지금. 이게 지금 50이고 12.5면 거꾸로 돼야 되잖아 매칭이 되려면. 좀 그림이 잘못되었어. 요거는 어쨌든 이해는 하지 그지? 일단 요 값을 바꾸려면 원래 n 값은 이렇게 돼. LP분의 LS 더하기 LP의 제곱으로 되니까 지금 딱 정해져 있어요. LS하고 LP가 정해져 있으면 컨버터 하는 값이 정해져 있어요. n이 12.5면 12.5에서 딱 정해져 있어. 그냥 이것만 이래 바꾸면 9배로 딱 정해져 있단 말이에요. 그러면 어떻게 바꾸냐고. 예를 들어서 n이 12.5에서 곱하기 4배로 바꾸고 싶다고. 그럼 어떻게 바꾸냐고. 9배가 아니고 4배로 바꾸고 싶어. 혹은 3배로 바꾸고 싶어. 어떻게 하냐고. 그거는 어떻게 하냐면 요 파트를 2개로 나눠. LS에다가 LSA에다가 LSB로 나눠. 그래갖고 LSB가 여기 지금 이렇게 두 파트로 이렇게 나눈다고. 이렇게. 두 파트로 나눠갖고 요거하고 나눠진 거하고 그 다음에 요거하고 합쳐갖고 요게 지금 요게 5고 요게 5니까 요게 4가 되려면 요게 5가 되면 되잖아. 그치? 이게 5면 이게 10 빼기 5니까 이게 5가 되고. 그렇게 해서 만드는 거야. 이렇게. 나눠가지고 요 부분만 컨버전 하는 거야. 거꾸로. 이해했지? 그 다음에 이쪽 부분은 안 바꿔. 그렇지만 아까처럼 패러렐로 바꾸면 같은 방법이잖아. 그지? 이게 전체가 아까 5였어. 그지? 패러렐이. 그러면 이거 10, 10으로 하면 10분의 10 더하기 10a 제곱하면 4잖아. 그러니까 이렇게 트랜스포메이션 해갖고 요거를 바꾸는 거예요. 요걸 이렇게 바꾸면 요게 이렇게 바뀌겠지. 거꾸로. 바뀌고 요건 L 스퀘어로 스케일링 업 되고 그 다음에 이쪽 부분은 N으로 스케일링 돼. N으로 스케일. 12.5 곱하기 5 하면 4 하면 맞네. 50이 맞네. 50. 이렇게 스케일링. 그리고 또 K로 스케일. 이런 식으로 하는 거야. 그래서 이게 적으면 이렇게 돼. 인덕티브 트랜스포메이션을 해버리면 요거를 이렇게 N으로 스케일링을 하고 이쪽은 N으로 스케일링을 하고 그 다음에 얘를 바꾸는 거예요. 이렇게 바꾸는 거. 알겠지? 이해했지? 그지? 이게 노턴 트랜스포메이션이야. 노턴이라는 사람이 정리를 한 거야. 이렇게. 요건 이제 제대로 됐네. 그지? 요거는 지금 임피던스 를 이제 줄이려면 RL이 200ohm이야 지금. 근데 이게 지금 K배로 지금 스케일링을 하고 싶어. 내가 K배로. 그러면 어떻게 하냐면 얘를 지금 2개로 이렇게 스플릿을 해. 2개로 스플릿을 해가지고 얘를 바꾸는 거예요. 얘를. 이거를 바꿔. 이거를 이렇게 바꿨어. 이렇게 바꿨어. 그 다음에 이쪽 바꾸지 않는 이쪽은 어떻게 해야 돼? N배로 만들어야 돼. 그치? N배 만들어야 되니까 아까 K분의 1로 했으니까 이건 K분의 1로 이렇게 합니다. 얘도 똑같아요. 그지? 얘도 스케일링 다운 하는 거. 이거 2개로 나놓고 그 다음에 어떻게 하지? 요거를 바꿔야 돼. 그지? 요거를 이렇게 샥 돌려. 이렇게 돌리고 그 다음에 이쪽 부분 스케일링 안 되는 부분은 그냥 놔둬. 스케일링 안 되는 부분 그냥 놔뒀지. 아까도 스케일링 안 되는 부분 그냥 놔뒀잖아. 그러니까 요거는 이제 이쪽이 스케일링 되는 부분만 있으니까 어쩔 수 없고 요거는 이제 수합하는 거니까 요거는 이쪽이 스케일링 안 되는 부분이니까 그냥 놔두고 요거는 이제 루트 K분의 1로 만들어. 루트 K분의 1. 그럼 요게 K로 이렇게 스케일링 돼요. 그래서 이걸 정리를 하면 이렇게 돼요. 지금 이건 뭐 C든 L이든 똑같아. 이거를 지금 스케일링을 하면 거꾸로 이렇게 만들어. 스케일링을 거꾸로 만들고 그 다음에 여기 나머지는 N배로 해. N배. N은 이렇게 되고 시리즈 패러렐 시리즈. 그지? 자, 얘도 똑같아. 그지? 요것도 잘못됐네. 요거는 지금 어떻게 돼? 요 LP지, LP. 그지? LP야, 그지? N이 LP. LP야. 그래서 지금 LSLP가 있으면 스퀘어 루트의 LSLP로 바꾸고, 이거는 이쪽은 안 바꾸는 부분이니까 N으로 스케일링 해야지. N으로. 그지? 이렇게 돼. 이제 파셜 트랜스포메이션도 똑같아. 그지? 내가 이거를 이제 스케일링을 파셜로 해가지고 어떤 값을 바꾸려면 지금 이렇게 바꿔야지. K 지금 K의 RL이고, 이건 K배로 스케일링이 되고, 그 다음에 K만 일보부시키고 나머지는 이제 여기다가 넣는 거죠. 여기다가. 원래 CP 빼기 N만큼 빼고, 그걸 다시 K로 스케일링. 이쪽이니까. 이쪽은 K로 낳는 거니까. 스퀘어 루트. 이것도 같은, 이것도 이제 패러렐이니까, 이건 이제 이렇게 해야지, 이렇게. 이거는 도메인이, 서세턴스 도메인에서 인덕턴스를 빼는 거니까. 그래서 이런 식으로 해서 여러분들이 노턴 임피던스 트랜스포메이션을 한다. 이해를 하면 되고. 이거 이제 하이트로야, 하이트로고. 여기도 또 틀렸네. 여기도 LS. 지금. 여기 LP지, LP. 이거 LP야, 이거 LP. LP야. 그리고 이케이션 쓰면 돼. And this is a dual resonance transmission line matching network, which was recently reviewed by me. And this is also interesting. And actually, this is this was originally, proposed by Ha Wang when he was a PhD student under, the advisory of Ali Hazmiri in Caltech. So basically, lambda for transmission line can be useful, right? So to transform, this impedance to, make an inversion. So typically we use a lambda 4, and there are two poles. Actually, this pole is a two pole. This pole is two pole, and this is four pole actually. Anyway, so this is a widely used matching network of wideband matching. So what he proposed, what the authors proposed is they just implement this using transformer. So the resulting transformer architecture is this. Okay. So basically, previously we just used this form of equivalent circuit. But if you just make a, if you just move this part to here, you can just use 1 minus K L1. Previously, it was like this way. You can just move this to scale, K scale. Okay. Then you don't have this. You don't have anything over here. Okay. This is another expression. This is exactly the same actually. 1 minus K L1 in K L1. And ideal transform. Same. So he used the second equivalence. So by transforming each, so as you can see, they use the this is actually lambda for transmission line. They just use the equivalent circuit given by this. Right? Let's say this is L. This is over C. Right? Then what is LC? So Z naught right here. GM equals to square root of LC. Okay. And beta is right. Beta is what? Omega square root of LC, right? Okay. Which is what? Beta L is lambda, right? Beta L is actually pi over 2. This is lambda of transmission. So beta is lambda over 2, and L is lambda of 4, right? Then it becomes pi over 2. Okay. So equivalently, you make omega square root LC equal to what? Pi over 2. Okay. Then you can choose from this and this. You can choose L and C values, right? This is L and C. Okay. here CM1 is just a half of C. Then you just use the Norton transformation like this, LM and convert it, and just use the L and L factor, right? As we've seen right before, we just do like this way, just perform the Norton transformation. Here, this n is actually square root of n. So previously LP and LP plus LS scale is here. We just say n scale. Previously it was k, right? So expression is somehow different, but design concept is same, right? Understand? That's why they use L scale, not k. But same, right? K is just n scale. 우연아 이해했냐?
알겠습니다.
태훈아 이해했지? 뭔 말인지.
네, 있습니다. 네.
그래서 똑같잖아, 그지? 그래서
네.
just 보면 똑같아. So since you just merge this together, right? Here, right? So eventually it shows looking like this. Okay, and also for this matching network, right? This is exactly same with this, right? So you just transform like this for this. Okay, so L prime is K M square LP. This is LM prime, and this is a L2 prime is just this is L2 prime, right? L2 prime is a KM square LP. Okay, so eventually, since there exists turns ratio 1 to n, right? This is effective turns ratio. The effective turns ratio is actually n divided by coupling coefficient. This is effective turns ratio. Okay, so have to use the effective turns ratio when k is not 1. Okay, this is important. So with this configuration, right, this part will be scaled down by n, right? This nkm. So this is a scaled version, scaled by n effective. N effective scale is a scaling factor, right? So this is original one, and this is a scaling factor divided by scaling factor n effective, which is this. Okay, that's why you get those, and this is also scaled. Okay. All right. Homework 8-2. Construct a dual resonant T-line matching network with RS equal 10. C1 is 15 femtofarad, L1 is 100 picofarad, RL is 50, C2 is 50 femto, L2 is 100 picofarad and 30 gigahertz using ideal transmission line and passive component. Convert the above network into transformer-based dual resonance circuit. Okay, with the RS prime equal 100 ohm at 30 gigahertz. Constructing as below. Okay, just use the ideal transformer and put Km and N. That's it. If you have more time, because those must be useful in designing your own circuit in real project, you may just convert it into real transformer, but that's an option. Okay, you may just use ideal transformer and ideal values. And for K, please choose K equal to 0.7. Okay. All right. So we have another one. Okay. So Bode-Farmer criterion is very simple, right? So for a given matching condition, right? For a given matching condition, The matching is always a trade-off between bandwidth and quality of matching. So for example, if bandwidth is wide, then the minimum level of matching is getting worse. So if bandwidth is wider, matching is more worse. If bandwidth is narrow, matching quality is become better. Okay, this is a Bode-Fano criterion. You cannot achieve, very good matching with a very wide band. This is impossible. It's because of quality factor Q, right? Q is just a ratio of this, right? How can you achieve, very low Q with a large ratio? So depending on the, load configuration, the limitation is expressed like this. But at the end of the day, the physical interpretation is the same. If bandwidth is wide, then the gamma is worse. Okay? Yeah, that's it. Okay, let's wrap it up. Thank you. 수고했어요.
감사합니다.
감사합니다.
감사합니다.